welcome all for this lecture. We are considering Bode plots. In previous lecture, we have seen that if the transfer function given in the time constant form, what is the main advantage we will get in the Bode plot is, as we are taking logarithm, all multiplicative terms become additive. So, when the transfer function is given in the time constant form, separate terms we have seen how to draw the Bode plots and then we can combine it. So, which components or which separate things we have seen? First we have seen that if constant gain is there, how to draw. Then we have seen that poles at origin, so 1 upon j omega raised to r. So, r poles at origin. Then we have seen how to combine k upon j omega raised to r. Then we have seen poles on real axis. Then we have seen zeros on real axis. And now we have to see complex conjugate poles and complex conjugate zeros. Complex conjugate poles and complex conjugate zeros. So, here we have seen that the transfer function, first we will see for the complex conjugate poles. For the complex conjugate zeros, just we have to consider instead of minus to plus, because it is at the numerator and poles are at the denominator. So, consider the complex conjugate pole. So, we will see here complex conjugate pole. How to draw Bode plot for the complex conjugate pole. So, we are considering the transfer function g j omega is equal to 1 upon 1 minus u square plus j twice zeta u. I think we are familiar that if the complex conjugate pole is there, we are representing a square omega n square upon a square plus twice zeta omega ns plus omega n square. Then what we are doing? Divide this omega n square both numerator and denominator. So, we will get here 1 upon, replace s by j omega. So, you will get here j omega upon omega n bracket square plus twice zeta omega n j omega and upon omega n square. So, what we will get, this omega n will get cancel plus 1. So, we will rearrange it, we will get here 1 upon 1 minus omega upon omega n bracket square, why j square minus omega upon omega n bracket square plus j twice zeta omega upon omega n. Check it how we are getting. Divide both numerator and denominator by omega n square. So, what we will get? Here it is 1, here it is 1. S square replaces by j omega as we are considering frequency response analysis. So, j omega upon omega n bracket square dividing by omega n square. Divide this term by omega n square. So, you will get upon omega n and you will we can write it like this. Now, replace it by u as the normalized frequency, where we are considering u as omega upon omega n. So, when it is omega upon omega n, what you will get it is 1 upon 1 minus u square plus j twice zeta u. The same thing is written here. 1 minus u square is your real part, and so it is written in this way. This is your real part, this is your imaginary part. So, what is u? U is omega upon omega n. So, the transfer function which we know in time domain, that we are converting it in the frequency domain by replacing s by j omega and representing it properly. So, that we will get the transfer function for the complex conjugate pole as 1 minus u square plus j twice zeta u, where u is equal to omega upon omega n. I think there is no doubt now. Next, what we are considering to draw the Bode plot for the magnitude plot. (20 log of g j omega). 20 log of g j omega, which we can write here is 20 log of magnitude of 1 upon 1 minus u square plus j twice zeta u. Okay. So, what is the magnitude you will get here? 20 log of magnitude of this is complex term. So, how will you write here? Magnitude of this under root real part square plus imaginary part square. So, what you will get here is 1 upon under root 1 minus u square bracket square plus twice zeta u bracket square. Is it okay? Magnitude of this we can write real part square plus imaginary part square. Take logarithm of this. So, what we will get here? 20 log of, I can write the same as 1 minus u square bracket square plus twice zeta u square, and this is minus half under root and it is at the denominator. Simplify it further. So, minus half into 20. So, you will get minus 10 log of 1 minus u square bracket square plus 4 zeta square u square or twice zeta u bracket square. Now, this is the magnitude plot which we can consider 20 log of g j omega. Now, as usual we will consider the whole frequency range in two regions, one is the low frequency region and one is the upper frequency region or high frequency region. So, which is the cutoff frequency here? The normalized frequency u. So, consider u is far less than 1. So, what is u means? Omega upon omega n is far less than 1. Then what will be the effect? Here we will get, if u is far less than 1, minus 10 log of u is far less than 1. So, you can neglect this. So, you will get this term is 1 and u is far less than 1, its square. So, far less than 1. So, neglect that. So, what you will get? Minus 10 log of 1, that is 0 dB. Approximate plot which we are considering by assuming that u is far less than 1. Now, consider u is far greater than 1. What will happen in that case? Consider u is far greater than 1. Then what will happen here? Minus 10 log of, see, u is far greater than 1. So, neglect this. So, what you will get? Minus u square bracket square. So, you are getting here u raised to 4. So, compared to u raised to 4, u square is small and so neglect it. So, what you will get here is minus u square bracket raised to 4. So, the same I can write here is minus 10 log of u raised to 4 or we can write here is minus 40 log of u. Check it. As u is far greater than 1, neglect 1. So, you will get minus u square bracket square. As u raised to 4 term is there, u square is negligible. So, neglect that. This is approximation. We are considering this for drawing the asymptotic plot. Okay? So, you will get here minus 40 log of u. So, this is for drawing the asymptotic plot. So, I will just write here to one side and then I will rub here. So, when u is far less than 1, our magnitude plot is 0 dB, and when u is far greater than 1, magnitude plot is minus 40 log of u. Okay. So, keep it aside. Now, we will try to draw it. Okay. So, x axis is logarithmic scale. Use semi-log paper. While drawing here, I am using logarithmic scale. So, just omega. This is starting point 0.1, next is 1. So, 0.1 to 1, you will get the frequencies as 0.1, 0.2, so on 0.91. Next is 1 to 10, that is 2, 3, 4 like that. Next is 10 to 100, that is 20, 30, 40 like that. So, logarithmic scale we are using and we will get it like this, while y axis scale is linear scale and we can write here is 10 dB, 20 dB in that way. Here minus 10, minus 20, minus 30, minus 40. Okay. Now, u is your corner frequency. So, consider somewhere here is u, that is here u is 1 means omega is equal to omega n, u is equal to 1. So, when the frequency is less than, u is far less than 1, we are getting it 0 dB. Meaning is that you will get the Bode plot, asymptotic plot 0 dB here. This is 0 on dB scale. So, 0 dB. When u is far greater than 1, it is minus 40 log of u. So, how will you find out this? Actually, we have seen, I am repeating it again. Consider u is 1. So, what is the value at that? So, at u is equal to 1, this value you will get 0 dB. When u is 10, what you will get? U is 10, log of 10, it is 1, at that time it is minus 40 dB. So, this is the change in frequency is 1 decade. So, this change is 1 decade. Within 1 decade, change is minus 40 dB. So, how will you represent here? This is u is equal to 1. I want 10 times u. So, somewhere here you will get u is equal to 10. At 10, it is minus 40 dB. So, represent that point minus 40 dB at u is equal to 10 and then connect it by a straight line. So, this point and this point you connect it by a straight line. So, connect it by a straight line. So, what you will get here? Slope of this line, slope of this line is minus 40 dB per decade. Slope of this line is minus 40 dB per decade. And we can draw the asymptotic plot like this. Now, we have seen that this is the approximation. So, whenever we are considering the near to 1, there is error. So, how will you calculate that error? That is important thing. Okay. So, we will see now how to find out error, and then that error we will represent properly. Okay. So, try to calculate now error. So, how will you calculate error? Error is equal to actual value minus assigned value or approximate value. Okay. So, what is actual value? So, error is equal to, what is actual value? Minus 10 log of, check it what we have seen, it is 1 minus u square bracket square plus 4 zeta square u square. 4 zeta square u square. This is actual value. When we are considering u is far less than 1, what is assigned value? Assigned value is 0 dB. So, minus minus plus you will get 0 dB. Okay. So, this is the error. When you are considering u is far greater than 1, what will be the error? Error will be, this is actual value, minus 10 log of 1 minus u square bracket square plus 4 zeta square u square. This is actual value minus minus plus 40 log of u. Actually value which we are considering in this plot is minus 40 log of u. So, this is your error. So, you have to find out what is the error at u is equal to 1. Okay. So, when u is equal to 1, what is the error? You will get the error is, so at u is equal to 1, error is minus 10 log of 1 minus u square bracket square plus 4 zeta square u square. This is the error. So, what you can observe here, as it is u is equal to 1, what you will get? U is equal to 1. So, you will not get this term, okay, plus 4 zeta square u square. So, I can write here directly the value is 4 zeta square. Or if I am considering twice zeta, I will get here twice zeta square, I will get minus 20 log of 2 zeta. Whatever may be writing, if this is your formula, what it indicates? It is fully dependent on the damping factor. That is the main thing. It is fully dependent on the damping factor. So, consider now zeta is 1. If so, different values of zeta you consider and find out the error. If zeta is 1, what you will get? Minus 10 log of 4. So, minus 10 log of 4, the value you will get somewhat. So, check that value, so, minus 10 log of 4. So, the value is somewhat minus 6 dB. So, you will get this value is minus 6 dB. So, actual substitute value of zeta. So, at zeta is equal to u is 1, zeta is 1, you will get this error. For different value, so for different values of zeta you can substitute, find out. Suppose zeta is very small, 0.05, then how much is your error? You will get the error is, substitute zeta is 0.05, its square and its value you will get is plus 20 dB. So, like that you can draw separately the error plot and that error you can represent on the magnitude plot. Okay. So, suppose now I am considering zeta is 0.05. So, I think it is better to draw the separate error plot and then correct the asymptotic plot. Okay. So, I will try to draw here the separate error plot. Okay. So, this is error plot. Consider this as 0.1, 1, 10 omega. This is 10 dB, this is 20 dB, this is minus 10, minus 20. So, at 1, when zeta is 1, what you are getting it? Minus 6 dB, that is you will get somewhere here. So, as you are going at 1 it is maximum, as you are going towards 0 you will get less and less error. As you are going away from this, less and less error, that we have seen for the actual values which we are considering. So, you will get the values somewhat like this. So, this is 0 dB, as you are going away you will get nearly 0, and so you can represent it somewhat like this. So, this is when the value zeta is equal to 1. Less than that, suppose 0.8, then what you will get? The substitute the value of zeta is 0.8, you will get the value is minus 4 dB. So, you will get somewhere here value. So, this is for zeta is 0.8. Okay. Then, when we are considering zeta is 0.6, zeta is 0.6, you will get some error is positive and then it becomes, so actual substitute and then you can find out, you will get the error somewhat like this. So, this is when zeta is 0.6. So, in between you will get it like this, and then as you are going 0.6 to 0.5, 0.4, 0.3, what you will get is it will go on increasing, and when zeta is 0.05, what you will get is the maximum error 20 dB, and then you will get it like this. So, maximum error you will get when zeta is going towards 0. So, this is when zeta is 0.05, and in between you will get, as it increases, you will get the variation is somewhat like this. So, while drawing actual plot, you have to substitute the value of zeta and calculate how much error is there, and you have to correct it. So, how will you correct here? At u is equal to 1, if zeta is 0.5, the error is 20 dB. So, you will get here actual plot will be maximum error, then error goes on decreasing and it is connected to the asymptote. When zeta is greater than 0.05, you will get less error, like this, and when zeta is 1, what you will get? Minus 4 dB, and then draw a smooth curve like this, sorry, minus 6 dB, and then draw a smooth curve. So, this is when zeta is, this is when zeta is 1, this is when zeta is 0.05. So, the main thing which you can observe here, complex conjugate pole, that the slope is minus 40 dB per decade. At u is equal to 1, error is maximum, and that error is fully dependent on the damping factor. Some when it is less than 0.3, you will get positive error, and otherwise you will get negative error, and the as per the substitution of the value of zeta, whatever value you will get, that you have to add. So, this is the corrected Bode plot, magnitude plot for the complex pole. Clear? So, what we have done for drawing the Bode plot, first we are considering u is far less than 1. Okay? So, u is 1 here. So, when u is 1 here till that it is 0 dB. After that it is minus 40 dB per decade. This is approximate plot or asymptotic plot. But near to u there is error, because you are considering u is far less than 1, u is far greater than 1, then you will get that error. But here you will get some error, and that error is maximum at u is equal to 1, and so you have to correct it by calculating error. So, calculation of error gives us that actual value minus 10 log of 4 zeta square, and so we can calculate it at u is equal to 1. So, this is at u is equal to 1 and different values of zeta we are considering. When u is changed, zeta is changed, your value will change and you will get it in this way. Okay. This is all about the magnitude plot. If the complex conjugate zeros are there, what is the difference you will get, or you can observe here that the term which is in the denominator will be at the numerator. So, 1 minus u square plus twice zeta u is at the numerator. So, what you will get, till u is equal to 1 it is 0 dB, after u it is plus 40 dB per decade. That is the change. Instead of minus 40 dB per decade, it will be plus 40 dB per decade. And then what you will get? This error graph will be exactly mirror image, because this term is instead of at the denominator will be at the numerator. Okay. So, where it is the error positive, you will get negative, where it is negative, you will get the positive error. Now, we will consider phase plot. So, I think now the magnitude plot you understood it properly. Now, consider phase plot. So, for the phase plot, phi is equal to minus tan inverse of, why minus? Because this is at the denominator. What is the formula? Imaginary term upon real term. So, what is imaginary term? Twice zeta u upon 1 minus u square. So, phase angle is, you will get twice zeta u upon 1 minus u square. First consider that zeta is equal to 1. So, as zeta is equal to 1, you will get twice u upon 1 minus u square. Consider u is far less than, or u is tending towards 0, and we are considering zeta is 1. What will happen that case? Zeta is 1, u is tending towards 0. So, tan inverse of 0. So, phi will tend towards 0. When u is equal to 1, see, when u is equal to 1, what you will get here? It is infinity term. So, phi is equal to minus 90 degrees, and when u tends to infinity, you will get phi is equal to minus 180 degrees. So, we will try to draw it. So, this is for zeta is equal to 1. So, angle we will consider 0, then this is minus 90 and this is minus 180. Minus 90 degrees, this is minus 180 degrees. Okay. So, at u is equal to 1, it is 90 degrees. And as u is increasing, you will get it is going towards minus 180. It is not minus 180, going towards minus 180. Otherwise, it is going towards 0, and the function is tan inverse. So, not a straight line, but you will get the function somewhat like this. Tan inverse function at u is equal to 1, it is minus 90 degrees, otherwise it is going towards 0, it is not 0, it is going towards 0 because the frequency is 0.1. So, it is not 0, and we will get the plot is like this. What will be the change as zeta value is, we are considering between 0 to 1. So, what will be the change? How will you draw that change? See, when zeta is equal to 0.05, you will get here a sharp curve somewhat like this, and in between you will get the value. So, suppose for different values, a particular value which is, so we are considering this first value is zeta is equal to 1 and this is for zeta is 0.05. In between you will get the magnitude plot is somewhat like this. Okay. As per the values of zeta, you will get the value, magnitude plot is like this. So, for the magnitude plot, the phase angle is minus tan inverse of twice zeta u upon 1 minus u square. So, it is again dependent on the damping factor. So, when the damping factor is 1, you will get just the tan inverse function, but when the damping factor is less than 1, you will get zeta is contributing some effect and you will get a sharp curve when zeta is nearly 0. In between 1 to 0, you will get different values. We can represent it somewhat like this. So, this is the phase plot. What will be the change if complex conjugate 0 is there? Instead of minus tan inverse, you will get plus tan inverse, because the term is at the numerator. So, you will get positive angle or the plus angle. Okay. So, that is the change only when you are considering complex conjugate zeros. Okay. So, I think we have seen separately each a part in the transfer function, and we have seen how to draw the magnitude plot and phase plot. So, now we will consider general procedure for constructing Bode plots. So, I think I will rub this and just we will see how to draw the Bode plot, general steps. Okay. So, all these parts we have seen. So, what we can do is separately we can draw the magnitude plot, but while considering as an example or whole complete transfer function, we have to combine effect of all. Okay. So, we will see now general procedure for constructing Bode plots. For constructing Bode plots. So, one by one we will see what are the steps. So, whenever the example is given, it may be in the time domain, then what you have to do? You have to convert that time domain to frequency domain. So, how you are doing that? Replace s by j omega. The transfer function may be in pole 0 format. What you have to do? Convert it in time constant form. So, the first step is rewrite the sinusoidal transfer function, that is in terms of j omega in time constant form. This is the first step. So, observe what is your transfer function. Time constant form. So, it may be given in the time domain, you have to represent it in the sinusoidal transfer function, that is replace s by j omega. If it is given in the pole 0 form, convert it into time constant form. So, first observe the given transfer function. If the given transfer function is not in the proper form, rewrite it in the frequency domain or the sinusoidal transfer function in time constant form. Next step is identify corner frequencies. Identify corner frequencies. So, corner frequencies associated with each part in the transfer function. Meaning is that these are the separate parts, you find out the corner frequency for each part or each component, and each part or each factor you can say, because we are considering it in terms of factors, each factor in the time transfer function. Each factor of the transfer function. Third step is knowing the corner frequencies, draw the asymptotic magnitude plot. Draw the asymptotic magnitude plots for each term. One care you can take here while drawing the asymptotic plot, you arrange the corner frequencies in ascending order. So, when you arrange it in the ascending order, what you will get is till that corner frequency it is 0 dB. So, when you are considering next factor, till that it is 0 dB. So, no contribution of that factor in the Bode plot. Okay. So, draw the asymptotic magnitude plots separately for each factor and then combine it together, or we can see while solving the example how we can do this. That is, instead of drawing it for each factor, considering it in the ascending order, we can draw particularly. This is asymptotic plot, that is approximate plot. So, you have to find out error graph. So, error graph you have to consider to draw the actual. So, error graph can be used to correct the asymptotic plot. So, how much is the error? Accordingly you can correct and you can draw the Bode plots. So, next step is correction in the, determine the correction in the asymptotic plot. Okay. Next step is draw the smooth curve, draw the smooth curve through the corrected points for each factor and combine it together. Okay. So, draw the smooth curve through corrected points, through corrected points and then combined effect you can see. So, this is the magnitude plot, this is the log magnitude plot. Next is we have to draw the phase plot. So, what? Draw the phase angle curve for each factor. And combine it. And combine it to get the. So, combine means what we are doing? Algebraically add all this to get the total phase plot. Combine it to get total phase plot. So, this is the general procedure. So, when we want to draw the Bode plot, there are two plots. One is magnitude plot, one is the phase plot. Magnitude plot, first step is you draw the asymptotic plot and then determine the correction in that asymptotic plot and draw it. In the phase plot, separate terms you can draw the phase plot and then algebraically add these values to draw a smooth curve for the phase plot. Okay. So, these are the steps. We will see by using this procedure how to solve or how to draw the Bode plots by considering a particular example. Okay. So, today we will stop here.